Bueno,
Hi.
hello guys. Yeah, maybe actually even starting even a little bit in Spanish, I don't know. Buenas tardes para los que están mirando desde Argentina. Good afternoon for the guys potentially in Europe. Almost good evening now. Welcome to this talk that we will have with Agnieszka Słowik and Celia Bel. Here I would like first to introduce Martín Palazzo, so from Argentina. Hello, Tincho.
Hello, how are you? Hola a todos, ¿cómo están? I will do it in English and Spanish. First of all, thank you for joining us. We are super happy to host this talk, this seminar from ClusterAI in Buenos Aires, Argentina. ClusterAI is the machine learning and data science course at the National University of Technology in Buenos Aires. And we are working with Matías and other colleagues in this teaching process, but also in the spread of the community and some ideas, point of view, histories, and a lot of things to show that the exchange of these ideas between the colleagues in machine learning community is super important. So we want to put in contact researchers and students and professionals from Argentina, but also from other regions like Europe or South America. So we are super happy to having you, and thank you for joining us.
Yeah, and actually, maybe let me ask people over there. Like if you are there in the YouTube stream and you can comment, maybe it would be great to know where are you now actually, which city, country. So even maybe if you want to share your affiliation or some other comment, please feel free to add that into the comments on the right-hand side. Sorry, Tincho, for interrupting. Yeah.
No, y aprovecho, I will do a quick explanation in Spanish also. Bienvenidos a ClusterAI, al curso de Ciencia de Datos y Machine Learning de UTN Buenos Aires, donde hacemos un esfuerzo bastante grande en abrir un montón de conocimientos, pero al mismo tiempo de fomentar la comunidad entre actores en la región y en otros continentes. Hoy es con gente de Europa, pero mañana puede ser África, Asia, Norteamérica, Oceanía. Estamos súper abiertos a eso y la idea o lo que buscamos es que todos se puedan acercar y debatir y conectar. Voy a switchear, voy a cambiar a inglés. Mati, I don't know if you want to introduce our speakers.
Yes, exactly. And maybe just to say that it seems that we already have people from Uruguay, from Germany. So thank you guys for commenting there. Let's then introduce now our guest and host, actually, Aya and Celia.
Hi.
Hello, Celia. Hello, Aya. Yeah, and thank you for joining us. I guess we will now let you actually start, but if you want just to say a few words before starting with Aga's talk, feel free.
Yeah, I guess a big thank you for having us. I mean, Aga, we are all super thrilled to hear more about your experience. I mean, knowing that you have been at Mila, at Facebook AI, and you are doing your PhD in Cambridge on a super exciting topic. So very, very thrilled to hear more about it. So I guess yeah, let's go for let's deep dive.
Thanks a lot for introduction, Celia. It's great to meet you, and thanks, Matthias, for inviting me. Hi, everyone. I'm currently in Cambridge. I'm happy to meet you, but yeah, ideally next time I would like to be to visit Argentina in a non-virtual way. So let's keep the fingers crossed that that's going to happen. And my talk is going to be about out-of-distribution generalization in image classification. So this is a subset of problems in machine learning.
Good. So I actually will then let you with the guys. So with the people here, I will just then put the slides on. Okay. So
all right. Oh, that's great.
Second, and we will then be back after the presentation for hearing like the questions and answers. Thank you.
Okay. Thanks. Okay, right, so let's start. The talk is going to be about out-of-distribution generalization in image classification. This talk doesn't assume any prior knowledge in machine learning, so I'm going to start by just explaining the title. I will briefly say what image classification is and what out-of-distribution generalization refers to, and how these two relate to each other. Then I'm going to talk about two research projects that I have worked on. They both contribute to this idea of understanding and improving out-of-distribution generalization in machine learning, broadly speaking. But on the high level, they differ in this way that the first one is more concerned with how we are training an algorithm, for example, a neural network. And the first one is more concerned with specific ways of designing an algorithm itself. So that's a high-level distinction. I will talk about it more later. And then I will conclude and I will briefly mention future avenues for expanding these projects. Right, so let's start with cats and dogs, the standard example. In image classification, an algorithm, typically a neural network nowadays, learns to approximate the function between input images and image labels. Here we have a simple example of distinguishing the images of cats from images of dogs. So in this example and in the rest of my talk, I'm going to be focused on supervised learning. So this is a way of using past data, which is already labeled, in order to train a model. Then it's going to be applied to unlabeled data, to a future data. And we are most interested in the performance of this model on this new data, right? Not only on the data that we have already collected and we already know what the labels are. And in the standard practice in supervised learning, usually we have some certain data set of images that might represent some, for example, some medical condition or even these simple cats and dogs images. And we are going to shuffle the data and then split it into either train, development, and test subsets or into just train and test subsets. And by shuffling, we are assuming that this data is going to be independent and identically distributed. And this is not the case in practice. So we are artificially creating this shuffling and in order to be able to use this assumption, because that's what some of the models require. But you will see that when we are talking about the actual past data and future data, this assumption doesn't hold. So what do I mean by this? For example, we might experience data scarcity. So in this case, we might not have enough labeled examples to be able to learn some robust association a robust model that we might be able to use to actually understand the relation between images and labels. So this is one type of an issue. Then we might have a population shift. So for example, in the domain of medical imaging, which is one of the most prominent applications of image classification, let's say that we gathered images of patients from a certain population, for example, from a certain age group. And then we trained our model, but then the future examples are coming from a different age group. So there might be a systematic difference between images that we used in training and the images that we are going to use to test our model, to actually use our model. So this is going to be population shift. And yeah, so then the decision boundary that we learned might not be useful anymore. Then we have, for example, prevalence shift. So in this case, we are not only concerned with the systematic differences in the images, but also in the label. So in this case, the label might be just 1 or 0. So for example, a presence of a certain disease or an absence of this disease. And so this is related to, for example, imbalanced case and control groups. And in probabilistic terms, this means that the conditional distribution given X, so given an image of some label, is different in the training and in the test set. Right, so the prevalence, because, for example, there might be more examples of the, let's say, of the disease in the test set. So this is prevalence as in the frequency also. This is the meaning of this word. And then finally, we have selection bias. So in this case, our labeled examples, they might only explain a subset of all of the possible examples that we might encounter in the past. So they only allow us to model an incomplete distribution, let's say. Okay, so now let me introduce some intuition about what is the relation between learning invariant stable features and out-of-distribution generalization. And also let's introduce this idea of using multiple environments under different conditions to estimate which features might be invariant and robust. So let's say that we have repeatedly observed that water boils at 100 degrees of Celsius. And then we can use this observation to formulate a law, a physical law, between the temperature and the boiling point of water. However, a new experiment conducted in different circumstances on top of a high mountain might reveal that there's another factor of pressure, or another feature of pressure, which also affects the outcome of the boiling point of water. So by using information from these diverse environments, we can refine our model or refine our physical law to make it more robust, hopefully. So I hope this idea introduces some intuition on how we can make the model more robust by using multiple environments in different conditions. Right, so how does it actually work in image classification or in general in machine learning? Let me introduce one specific algorithm called invariant risk minimization. IRM loss function can be used to find a data representation on which a model is optimal in all environments. This is very important in the context of image classification, because if you think of images, the raw features or the raw properties of the data would be just pixel intensities. And it might be very hard to model meaningful statistical associations between just raw pixel intensities and the label of a cat or a dog, right? So there is a relation, but it's between some higher level representation of an object in an image and the label. So we are also interested in discovering this data representation, which is not given explicitly to us. So when it comes to the environments, this is very similar to the boiling water example. So these are just different conditions, and we assume that they might represent different training distributions. So there's, for example, in the IRM paper, there's a quite famous cows versus camels example. So let's say that we have a data set of images of camels and cows, and we know that some of the cows come from Switzerland and some of the cows, let's say, come from Egypt. So then the Egyptian cows are going to be more frequently seen on a sandy background, and the Swiss cows are just seen in the green pastures and mountains. And yeah, let's say we have also camels from different backgrounds. And in this case, these distinct environments, they can just correspond to different locations where these images have been taken. And each of these environments will come with specific biases. In this case, a bias of a certain background color. Right, so then we have error, because in all of the loss functions, so we need to minimize some error. This is very similar to the standard supervised learning procedure. We are minimizing error across all of the environments. And then the most distinct trick, basically where the difference lies when it comes to IRM, is this penalty term. So it measures how much the performance could be improved in each of the environments with a single optimization step. And this is introduced because the problem of finding the optimal classifier in all of the environments is actually a two-level constrained optimization problem, because we not only do we find the optimal data representation, but also the optimal classifier. So this is a trick to reduce this problem to a single optimization loop, as you see here. And without the IRM, without this penalty, a model in practice, it could minimize the loss by performing very well in just one environment, so just for images from one location, and poorly in others. And we add this term just to ensure that the model has converged in each environment, so that the learning is actually balanced across the training distributions. Okay, so here, just to wrap up, these are practical considerations for applying IRM. IRM performance depends on how diverse these environments or these datasets are. We need some prior knowledge about the dataset or some type of a meta-information to construct these distinct environments. And this is not always available, because if we just have a blob of images, then of course we might not even have the information where they come from and what the systematic differences might be. And this is quite often the case. So we need a certain a priori information. IRM might also lead to a higher training curve, but that's all right. So because we mostly care about the test future error, and there is no guarantee that IRM is not going to learn any spurious associations, because in some cases spurious associations might still be the strongest discriminators, right, across these environments. So because of this reason, it is very important to provide multiple and sufficiently diverse environments for IRM to work well. Okay, so in late 2020, I started working on a linear benchmark for understanding successes and failures of IRM and similar methods. And basically, the main conclusion is that the existing methods struggle even in linear instances of the problems that we encounter in the multidimensional space of images. So for example, example 2 and example 2s, this is a linear representation of this cows versus camels problem that I have described. And in this case, Oracle refers to the best possible performance, because this is an algorithm which already knows which features are spurious and which are invariant. And the remaining ones, these are existing, recently proposed algorithms. So it's IRM and then some more recent one. And we're also showing performance for error risk minimization, which is just the standard supervised learning method. And so we, unfortunately, only in example 1, IRM actually performs close to the Oracle. In example 2 and example 3, they are still quite tricky. So example 2, as I said, this is cows versus camels. And example 3, this is the case when we have a small invariant margin and a large spurious margin. So it is possible to learn to even achieve a 0 training error solution just by using this spurious environment-specific association. So this is a very tricky problem, and it turns out that it is hard even in the linear case. So before moving on to solving it in image classification, it might be worth spending more time on improving these algorithms in the linear domain, which is more interpretable and easier. Okay, so these are some just more ablation studies. So as you might expect, once the number of spurious features increases, the performance becomes even trickier. So clearly these algorithms, there's still quite a lot to be done. These results come from a workshop paper that I worked on and I wrote together with my collaborators from Facebook AI, and it is available on arXiv. So if you are at all interested in this topic, then I encourage you to check it out, and you can also reach out to me offline to talk more about it. Okay, so far, I have talked about the specific learning setup of using multiple training distributions instead of shuffling the data and pretending it's IID. And we talked about an example of a loss function that can be used to find an optimal model and optimal data representation across these training distributions. So this was one training scenario for trying to estimate a model that is going to be useful in out-of-distribution scenarios as well. So now I will change the angle a bit, but it's still going to be about out-of-distribution generalization with applications to image classification. But I'm going to briefly talk about changes in the structure of a model itself that can be made to encourage potentially a lower out-of-distribution generalization error. I'm going to show results using this simple visual question answering task, where we have such image just representing a simple geometrical shapes, and each image is paired with 6 questions. But it's fine, there can be any number of questions. But the main point here is that this task is very simple if we just use a standard supervised learning setup, and if we just care about the in-distribution generalization. So if we just gather this data and shuffle it and have some random train and test split, and if we're only going to evaluate our model on the same questions and the same colors and the same shapes, the same set of colors and shapes that we have encountered in the training set. But as it turns out, as soon as we introduce a new color shape combination in the test set, so for example, let's say that we had red circles and blue squares in the training set, so in the data that algorithm has observed when it was learning, and then we have red circles, then let's say we have a red square, right? So we have a color and a shape that both of them were seen in the training, but not in this specific combination. And it turns out that this is actually a very hard problem for neural networks, because they still don't really learn in a very intelligent way. So if we make this modification to this data set, suddenly the performance even of the best algorithms drops to around 50%. So this is basically still something that's still quite challenging. And you might imagine that if it is challenging even in this synthetic simple task, then it creates even more issue in real life images. Okay, so this is an overview of a model that I worked on together with collaborators from Mila. This is also 2020. And this was called neural function modules. And this is a new mechanism, or a new variant of neural mechanism. And it is based on this idea of dynamically choosing previously computed hidden representations, instead of processing the entire hidden state in a sequential way. So this is an addition to any type of neural architecture. So it can be used, so my collaborators used it for generative modeling or reinforcement learning. And there is a hope that this might improve out-of-distribution generalization, because it increases the specialization of individual layers. So again, if you're interested in talking more about the technical details, feel free to reach out to me online. And you can also check the archive paper. Okay, so now just some results. So this is, it doesn't mention the name of the data set, but it is the same data set that I have just shown to you. So it's the same data set of simple objects and questions paired with these objects. And essentially, it seems that introducing this way of dynamically choosing previously computed hidden representations, so allowing this option in a neural architecture, it does increase out-of-distribution generalization a bit. So then as you see, the more unseen combinations we have in the test data, the harder it becomes. But yeah, so NFM brings a bit of an improvement in this specific case. And then, so I was interested in seeing if it improves the result just because it increases the number of parameters, or then the model is becoming larger and it's more expressive, so it can express a more complex function. So because of this, I compared the effect of using neural function modules with the effect of increasing the model size in a brute force way. So in this case, double and hyphen, this refers to just increasing the filter size and increasing the number of layers. So this is increasing the model size without any conceptual changes in the structure of the model. So it does seem that the way this conditional computation is implemented in NFM, it makes a bigger difference than just increasing the size of the model. Okay, so yeah, so this is all work in progress. So I'm definitely interested in understanding NFM and NFM-like modular architectures more. Ideally, I would also like to work on the IRM-like method, which might work better for example 2, and so the tricky cows and camels problem, at least in the linear case. And on another hand, I am also interested in a different, let's say a different outlook on out-of-distribution generalization, which is to study using a discrete channel. So this is a bonus. And yeah, because in most of the neural networks, for example, in this NFM architecture that I discussed earlier, we are mostly using continuous layers because this is needed for backpropagations, because that's how we train neural networks. But there's also a very interesting area of research called emergent communication or multi-agent communication, which introduces different gradient approximation methods, but essentially a discrete channel, because let's say human language is discrete. So this relates to the idea of trying to make the neural networks communicate with each other in a similar way as intelligent biological systems communicate with each other. But on another hand, it also works as a regularizer. So there are some results suggesting that it might help in discovering these invariant stable features, because we are adding regularization, and potentially we might force neural networks to learn the invariant features, for example, in images. So this is an example of a task which is most commonly used in emergent communication. This illustration comes from a paper with a PhD student from Edinburgh. That's also from the last year. And in this case, we have two neural networks, a speaker and a listener. And the speaker observes some image and then describes the image to the listener in a discrete way. And then the listener has to point to the correct original image in the set of distractors. So distractors, they typically come from the same distribution. So these are just different images, which might look very similar to the input image. So that's how we train this whole system, and that's how the agents can develop a discrete language, which might also help us to help us to make these agents learn the invariant features. So there's a hope that then we can maybe apply it to out of distribution distractors and so on. So that's another area of research which I'm very interested in. Okay, so that's it. Thanks a lot. Feel free to ask any questions, and also feel free to reach out to me offline. Of course, thank you to my PhD supervisors and all of the collaborators from Facebook AI, from Mila, and from the University of Edinburgh. And thank you for listening.
Hey, Aga, a big thank you. That was super insightful. And there are actually quite some questions. So the first one would be actually, what is a linear benchmark?
Okay, so that's a good question. So this is a linear benchmark. It's a linear data set. So in this case, we had 3 specific linear problems. So linear because the data is linear and the decision boundary is linear. So if we have 2 of them were a binary classification problem. So it means that they are linear because there is a linear function, a linear decision boundary, which can separate the examples from one class from the examples of the other class. And then if we have a regression, then there is a linear function which models the relation between the observed samples and some continuous outcome that we care about. So in the sense that they are linear. Does it answer the question?
I guess so. The next question would be, what are the examples you evaluated the algorithm on? So I guess that was the slide when you were showing the different performance of the algorithm for the linear test. So example 1, 2, 3, and...
Right. So in this case, in this work, the main focus was understanding and improving onto distribution generalization, but the concrete outcome is this data set. So these are all of the data sets that we evaluated on. And S, so this S refers to just applying a linear transformation, just so that the problem is a bit harder. But it's basically a variant of these base problems, which are example 1, example 2, example 3. And I guess maybe the question relates to this this method, because I only showed results on one data set. So yes, so it was I only also applied it to another, another variant of the image classification task with symbols, it was called. So this is a bit similar to MNIST, which is just classifying digits based on images. I was also working on systematic generalization in this case. And apart from this, also my collaborators worked on an Atari reinforcement learning case and on generative learning. And there was also a variant of MNIST as one of the simplest image classification tasks.
Cool. New question for the neural function module. So the NFM is a combination of CNN and transformers, or what is?
Yeah. Okay. So as a result, after applying NFM to a convolutional neural network, it is a bit similar to sparse transformer. It can be applied to CNN, but it can be also applied to other neural networks. It can be also seen a bit as a form of a recurrent neural network. So actually, it is a bit hard to answer this question without going very much into technical details. But it is the most similar to a sparse transformer, I would say.
Okay, so it's a sparse transformer. Okay, another question actually I would be curious to know more about, it's not a technical question, it's more a personal one. I would be interested to know more about your personal story actually, and how did you start with AI?
Okay, thanks a lot. Right, so it's a bit of a complex and rocky story because until I was 18, so when I was in standard schools, I was the most interested in mathematics, but also in foreign languages and in writing and in philosophy. So I didn't fall into these typical distinct sets of science students and humanities students. So that's why for a while, it took me a while to figure out what I actually want to study. But then when I started studying computer science, I was immediately interested in doing something that would be at the intersection of science and engineering. And also at that point, I think I was interested in doing something that would be at the intersection of computer science and mathematics. So then it seemed like a very good choice. But then on another hand, what I also really like about AI or machine learning is that it also relates to so many real world problems, that it can actually be applied to make a difference in the world. Because I think for a sustainable career, you need to have this type of external, external motivation, the motivation of creating some value to the world or to people. So yeah.
Yeah, and I guess it's used everywhere now, so that makes complete sense. Yeah, I'm just checking if we have other questions from the audience. So I would also have another story about. Actually, you have been to different labs, right? You have been to, in Canada. You have also been to Facebook AI. How is it to the collaboration? How is it happening in those labs? And also, how is it to work abroad?
Mm-hmm. Right. Yeah. So machine learning research is quite international, but having said that, there is still a lot that can be done to make it even more accessible and even more international and diverse. I would say that maybe the country and even the university itself doesn't matter as much as the supervisor and the group. When it comes to these higher level differences, so I can tell you that, for example, PhD at Cambridge is more, I think it's more self-guided than in any other places, and it's also shorter usually because it's just 3 to 4 years. But then on the other hand, there are no strict requirements for the publication count, as there are at some places. Right, so basically, I think the main difference comes from the group and the supervisor. When it comes to deep learning, it is also important what sort of access to compute you have. And that's also, that's why some people also say that companies might be at an advantage here. It used to be also a factor that at some places it was the travel funding was limited, but at least now the silver lining to our current situation is that there are no travels, so it's cheaper. Basically, it's much cheaper now to attend conferences than it used to be. Because I remember it was such a huge issue to gather enough funding to go somewhere for a conference. But now it's much cheaper.
Now it's solved.
Okay. So I think. Yeah, that's it basically.
No, you were saying.
I definitely encourage working in different environments. I think that's a very enriching experience.
Yeah, I can imagine. And we have another question about a career path question again, which is if you were to start over again with data science and machine learning, in which topic would you start? That's a cool one.
Mm-hmm. Yeah, that's really cool. To be honest, I think it's hard to say if even in research is the right solution to just start with one topic and then stay, because I think there is some value in exploring. So even if you start with something that you're not entirely happy with, then it might still have some value later on. So it's hard to answer like this. I think what I would change. So I guess it is worth having research experiences quite early on. And for example, at my university, this wasn't the standard because I did my undergrad in Poland, in Kraków. So I remember that in the last year I had to push a lot, and it required a lot of my own initiative to be on some research projects. So I think maybe I would try to create such opportunities even earlier than only the last year of the undergrad. Because when I see people who are especially doing PhDs these days, applying for the first year, they usually have an experience very early on. So I guess maybe now, if I were starting now, I would have opportunities to start even earlier. But again, I'm not entirely certain that this would make it much better. So, yeah.
No, that's. I would also have a question about if you had faced any challenges in your journey. I mean, it's quite super impressive what you have done. So just wondering if there were those some challenges you faced.
Yes. So definitely, yes. The most recent challenge was actually my last when I went for my last internship to Montreal. I moved to Canada and to Montreal very shortly before the pandemic really started and the lockdown started. And yeah, I had a lot of issues. I was incredibly isolated and I guess prone to different types of issues. So then I had to cut my even internship short, and I came back to Cambridge, and I spent 2 months basically recovering from this. So yeah, so there were definitely challenges, and it's always it's usually the case that PhD is quite a rocky experience. But then on another hand, on a positive note, even in the similar time frame, I still had a positive work-related experience, because I was a machine learning tutor at AI for Good, and this was very nice. And this was also something that I found when I was at Mila, towards the end of my stay at Mila. So
actually, I saw you were doing. I mean, in your personal website, it's amazing how much you do. You are a mentor, you are a teacher, you are also like super active in many different associations, like this AI for Good. How do you handle all of this? That sounds like a lot.
So I am I am active at the department where I'm doing my PhD. So I'm teaching and organizing talks and representing students. And also I'm active in machine learning community as a reviewer and again as a teacher and as a mentor. I think it's a way of being a good citizen and giving back to the department and to the community. But it's also the thing that PhD work can be very lonely and abstract. So I think it also helps to have some social and human-oriented obligations, let's say. But yes, for example, teaching. This is a really cool thing. It's also a great way to learn, basically, and to become stronger in your field. But having said that, now I am past the midpoint of my PhD, so I'm trying to spend more and more time just on my own research.
Yeah, makes sense. I guess now it's really a lot of And what excites you most about your research work?
Right. So what excites me most? Yeah, that's a great question. So out of distribution generalization, it touches upon a lot of fundamental issues in machine learning or deep learning in the real world. So some of these issues are robustness, security, reliability, interpretability, data efficiency, and that's just to name a few. So it's very exciting to work on something that can have impact across multiple real-life domains. And two specific domains that I'm very excited about are communication. So I briefly talked about it earlier. So that's about simulating human-like communication between artificial agents, parameterized by neural networks. And also I'm very interested in, broadly speaking, medical applications, including drug design, improved diagnosis, medical image analysis. And I'm really excited about these domains because of how they relate to human life. And it's also great to see that machine learning is, as I said earlier, at the intersection of science and engineering. So it allows me to have a mix of both.
Yeah, you mentioned you were interested also in languages, so that was quite funny to see you are studying emergent languages from like different AI models. So that's super cool. So again, feel free for anybody to use the chat. It's really a huge opportunity that we can ask Aga any questions. And I will again use this opportunity because I am quite also, it's more of a technical question because there is now a bit of excitement with Facebook AI in the past days. And I was wondering, what do you think about self-supervised learning?
Yeah, so that's very interesting. That's also one way of improving auto-distribution generalization. So it's one of the most recent areas that I started reading about, meta-learning and self-supervised learning. So.
Okay, so it's another point. Right. So I guess.
No, I have two questions to Aga. The first one is, as you know, you have like a trade-off in the classical problem of variance and bias and too easy models or too complex. Do you see like a connection to this concept from the looking for the invariant features? If you put a lot of effort in probably in trying to generalize a lot, could you have like another type of error or trade-off that you are having in a loss or something? You find a connection to this trade-off of variance bias, but from the invariant perspective?
Yeah, that's a very interesting question. Yeah, so I think Yeah, I would need to think more about it. But if you use the IRM-like methods, it would seem that the bias is going to be reduced because we will have all of these different training distributions. Depending on the specific training distributions, we might have variance, the issue of the variance. But if we actually manage to uncover the invariant features, then in the ideal case, if this is a noiseless solution, then we would actually be able to escape this trap of the bias and variance error. But in practice, I think that I would imagine that bias is reduced thanks to using multiple training distributions.
Great. And the second question, probably Celia will be identified as well because it's more related to the biomedicine perspective than, as you know, in any problem that you have to sense data or to collect data, you have different type of sensors. And in biotechnology, biology, and it's not as standard as a camera, as a photograph camera. That, I mean, is more or less the same device in all around the world. So in other domains, the sensors are not so constant or so standard. Do you see some interesting applications in this, in biotechnology, biomedicine, that we have to deal today with different type of environments, even from the same problem?
Yes, yeah. So that's also an excellent question. There are a lot of papers that deal with scanners and medical imaging. So again, feel free to reach out to me and I can recommend them. So definitely, data coming from different scanners can be used as different environments or different training distributions. And this would be an example of I guess, population bias, because this is something that affects the image itself, not so much the relation between the image and the label, but just even the images are different, right? So I remember that at one conference I've seen results which showed some sort of medical imaging model and results, but then it turned out that actually there was a very strong spurious association coming from a scanner type, that all of the images that were belonged to a certain label in one of these scanners, they had, I think it was a frame or something like this. So it was very obvious that the way it actually worked was that it exploited the scanner-related spurious association. Yeah, so scanner data coming from different scanners can be used as each scanner as the different environment, and it is an example of a population bias.
Thank you. You are mute, Mati.
That's the classic COVID problem. Thank you, guys. I mean, it was impossible not to do it. So now that I guess you hear me well, I also wanted to jump in with a question. And I don't know if you can share a little bit, you know, of the collaboration process, how it looked like, because you know, I guess sometimes you are coding, sometimes you are writing, or kind of like approaching theorems, and then you need to exchange with people, like for the writing, for the code. And I just wanted to know how it looks like for you, if you can share a little bit with us, you know, and how you develop the ideas and the solutions to the problems.
Yeah, okay. Right. So yeah, now everything is remote. And I think it might be more difficult to start a collaboration remotely than in person. So that's one thing. And on the other hand, I think it's very important to state clearly your expectations and also your time availability at the beginning of the project. So even if other people are not very keen to do it, I think this is like a basis of a good collaboration. Basically, we are defining what we expect and how much time we can commit and what exactly we want to do. Because it's very common an issue that PhD students in machine learning or any researchers in machine learning, they often work on multiple projects at the same time. So it can be quite tricky. On the other hand, I think, so usually it ends up being the case that everyone does a bit of everything. So it is, I was never in a collaboration where I would only do writing or only do coding or only experiments. In the end, the way it turned out was that I was doing a bit of each of these things, and everyone was doing a bit of it. But it's also true that in research people are quite individualistic, so sometimes it can be very hard to split this type of work. But I think it's important to try to do it at the beginning. And also, I think that in my case, I did a lot of short-term collaborations. So I would also, like in hindsight, I think it might be also more useful to have a long-term collaboration. For example, I think the best case for doing a PhD is when someone has a very strong ecosystem and a strong group that with whom they can work for, let's say, 4 or 5 years. And these people are usually incredibly productive in terms of the papers and so on. So short-term collaborations are great because you can learn more and meet more people. But eventually, I think it's nice to at some point to build a lasting long-term collaboration.
Thank you.
Mm-hmm.
Thank you. I guess that was super, super informative and inspiring, Aga. Thanks for motivating us. And thank you, Matthias and Martin, for organizing the talk. So I will let you, I will pass it on you guys for the last words.
No, I mean, thank you again, Aga, Celia. It was very, very nice, to have this kind of like conversation, these sessions, and hopefully we will manage to have more and more frequently. So again, thank you, Tincho, also, and also to the people joining us. And I guess now this video will be online in YouTube. So for those that were not able to join us live, I guess they will be able to watch it later.
Yeah, the next meeting in Buenos Aires, please.
Yes, for sure. I mean, as soon as this COVID thing is over, let's organize that. Let's have Aga in UTN, and then we also show her a little bit around with Celia. So a lot of, especially Tincho, I guess that he's still there. He will have all the tips on the nice spots to visit.
Yes, because by the way, me and Matthias know each other from Peru. So, but I've only been to Peru when it comes to South America, and I would really like to visit other countries, Argentina especially. Yep.
Yeah, exactly. So it was the machine learning summer school in 2016,
I think.
Yeah, correct. Yeah, I mean this was an amazing summer school. We really met a lot of people that are working now. Also, I guess you also know Alfredo. You work in Facebook.
Yeah. So we talked. He's also applying for a PhD. Yes.
Okay, good. I guess we will also have Alfredo. So stay tuned. Potentially we will talk with him. So again, thank you guys. And I don't know if you want to close it, say something else, please feel free.
Oh, thank you.
Thanks a lot. Yeah, have a good Sunday.
Bye. Thank you very much. Bye-bye.